A single Ohio-class submarine carries 20 Trident II D5 missiles. Each of these missiles can be equipped with up to 8 independent nuclear warheads. This means that a single vessel, hidden somewhere in the vastness of the Pacific or Atlantic, holds more destructive power than all the bombs dropped by all sides during the entirety of World War II. Despite weighing over 18,000 tons when submerged and stretching 560 feet in length, nearly the size of 2 football fields, this machine is designed to be virtually undetectable. The United States Navy spends billions of dollars not to make these ships faster or more heavily armored, but to make them quieter. In the physics of underwater warfare, sound is the only currency that matters. If you are heard, you are dead. The Ohio class has served as the backbone of the American nuclear triad for over 4 decades, maintaining a constant, silent vigil. These submarines operate in 2 crew rotations, blue and gold, ensuring that the hulls spend nearly 70% of their life submerged and on station. They are self-sustaining ecosystems capable of generating their own oxygen and fresh water, limited only by the amount of food they can carry for the 155 men and women on board. However, as sonar technology and artificial intelligence tracking systems advance, the ocean is becoming more transparent. This reality has forced a $132 billion evolution into the next generation of underwater dominance, the Columbia class. But as we transition to this new era of electric stealth, one central question remains. How does a machine of this massive scale remain hidden in an ocean now filled with thousands of autonomous sensors? The Ohio-class ballistic missile submarine, or SSBN, represents the most survivable leg of the nuclear triad. While land-based silos and strategic bombers can be tracked via satellite, a submerged submarine disappears into 321 million cubic miles of water. To maintain this invisibility, the hull is coated with thousands of anechoic tiles, rubber-like structures that absorb incoming sonar pings rather than reflecting them. This ensures that the massive 560-foot structure appears as nothing more than a void or a biological anomaly to enemy sensors. The primary payload consists of 20 vertical launch tubes, each housing a 3-stage, solid-fuel Trident II D5 missile. These missiles have a range of over 7,500 miles and travel at speeds exceeding Mach 24. Despite this immense firepower, the submarine's strategic mission is defined by non-use. Engineers designed every system on board to support continuous at-sea deterrence. This requires a mechanical reliability rate that exceeds 99%. As these ships must remain submerged for up to 70 to 90 days at a time without surfacing or communicating. Inside the hull, space is managed with extreme precision. The Sherwood Forest, the nickname for the missile compartment, contains the 20 massive orange tubes that span 4 decks. The weight distribution must be constantly balanced. As the crew consumes food and supplies, or as water is distilled, ballasting systems automatically adjust to keep the ship perfectly level. This prevents any shifting of mass that could cause the hull to tilt, which would change the flow of water and create detectable noise. A single vessel holds more destructive power than all the bombs dropped in World War II. But how does it stay hidden in an ocean full of sensors? The secret is not just in the rubber coating, but in a radical approach to mechanical engineering that treats every moving part as a potential acoustic leak. In the deep ocean, light disappears within 600 feet, but sound can travel for thousands of miles. To an enemy sonar operator, the mechanical signature of a submarine, the rhythmic thrum of a pump, or the whine of a gearbox, is as identifiable as a fingerprint. To eliminate these sounds, the engineers designed the Ohio class using a technique called acoustic rafting. Instead of bolting the steam turbines and electrical generators directly to the hull, they are mounted on massive steel platforms, or rafts, which are then suspended on specialized rubber sound isolation mounts. These mounts act as high-tech shock absorbers, soaking up mechanical vibrations before they can reach the outer steel hull and radiate into the water. Every pipe and cable that exits these rafts must be flexible to prevent the transfer of vibration. The ship's main propulsion shaft is also a masterpiece of engineering. It uses a high-precision skewback propeller designed to minimize cavitation, the formation of tiny vacuum bubbles that collapse with a distinct popping sound. By controlling the pressure across the propeller blades, the submarine can move at significant speeds without alerting nearby acoustic sensors. The discipline extends to the crew's daily life. The ship operates under ultra-quiet conditions during patrols. In this state, the use of certain plumbing systems is restricted, and heavy doors must be closed by hand to avoid slamming. The deck is covered in specialized floor tiles to dampen the sound of footsteps. In the silent world of the deep, a dropped wrench can be heard for miles. Engineers designed this 18,000-ton machine to be quieter than the ocean's background noise. The art of silence keeps the ship invisible, but maintaining this silence requires a power source that never needs to breathe. The limit of its mission isn't the fuel, it's the psychology of the crew living inside a closed-loop nuclear environment. But the operational heart of the Ohio class is the General Electric S-8G nuclear reactor. This pressurized water reactor provides the ship with two critical capabilities: unlimited range and massive electrical power. Unlike diesel-electric submarines that must surface or use a snorkel to breathe air and recharge batteries, the S-8G allows the Ohio class to remain fully submerged for months. The heat from the reactor core generates high-pressure steam that drives two massive turbines for propulsion and two service turbo generators that provide electricity for life support, sonar, and weapon systems. The S-8G is a natural circulation reactor, meaning that at low power levels, the coolant can circulate through the core without the use of loud electric pumps. This feature is a primary reason for the Ohio class's legendary stealth during patrol speeds. Beyond propulsion, the reactor powers the ship's electrolytic oxygen generators, which split water molecules into breathable oxygen, and the desalinization plants that provide thousands of gallons of fresh water daily. The hull becomes a self-contained planet, generating its own atmosphere and water indefinitely. The endurance of the ship is limited only by its food storage and the mental stamina of the 155 crew members. During a typical 70 to 90-day deployment, the crew sees no sunlight and breathes only recycled air. To maintain morale and efficiency, the Navy utilizes a two-crew system, blue and gold, where one crew takes the ship on patrol while the other trains on land. This ensures the hardware remains at sea for the maximum possible time. And the submarine is a self-sustaining planet beneath the waves, but the limit of its mission isn't the fuel, it's the psychology of the crew. This nuclear heart provides the energy needed to remain hidden, but the true test of the ship's engineering occurs when it must interact with the surface. Launching a 60-ton missile from 100 feet underwater requires a perfect vacuum seal. But what happens to the ship's stability when that massive weight suddenly leaves the hull? Igniting a rocket motor inside a submerged submarine would be catastrophic, as the extreme heat and pressure would destroy the launch tube and compromise the hull. To prevent this, engineers utilized a cold launch system. When the command to fire is given, a high-pressure steam generator at the base of the tube ignites a small, solid grain charge. This creates a massive gas bubble that ejects the 130,000-pound Trident 2D5 missile out of the tube and toward the surface at nearly 50 miles per hour. As the missile breaks the waterline, sensors detect the change in pressure and ignite the first-stage solid rocket motor. This transition happens in seconds. However, the physics inside the submarine are equally violent. When a 60-ton missile leaves the ship, it creates a massive vacuum in the tube that is immediately filled by seawater. This sudden influx of weight, approximately 100,000 pounds of water, threatens to pull the submarine downward or cause a dangerous tilt. To counter this, a computerized hovering system instantly compensates by shifting ballast water between internal tanks to maintain a depth within inches of the target. Launching a missile from 100 feet underwater requires a perfect vacuum seal. But what happens to the ship's stability when 60 tons of weight suddenly leaves the hull? The coordination between the missile's flight computer and the ship's ballast control is a masterpiece of automated engineering. This mechanical ballet ensures that the submarine remains a stable platform for the remaining 19 missiles. Yet, even with this capability, the ship is useless if it cannot receive orders while deep in the abyss. If you're enjoying this deep dive into military technology, consider subscribing to the channel. And before we continue, leave a comment telling us which country you're watching from. It's fascinating to see how these machines capture attention from people all over the world. To remain undetected, a submarine must be a black hole for information. It never transmits radio signals that would give away its position. However, it must always be ready to receive an emergency action message, EAM. Standard high-frequency radio waves cannot penetrate seawater, so the Navy utilizes very low frequency, VLF, and extremely low frequency, ELF waves. These waves have massive wavelengths that can reach depths of hundreds of feet, but they require equally massive antennas to be captured. To receive these signals while remaining deep below the surface, the Ohio class deploys a buoyant wire antenna. This copper core tether can be up to 5 miles long, trailing far behind the submarine as it moves through the water. The antenna floats at a specific depth, acting as a sensory organ for the ship. Because the data transfer rate of VLF is incredibly slow, often limited to just a few characters per minute, the messages are usually short, coded strings that trigger pre-planned operational procedures. To remain stealthy, the ship must never transmit. But how does the commander receive the go code if the ship is 800 feet below the surface? The VLF tether provides the answer, allowing the submarine to stay connected to the National Command Authority without ever needing to raise a mast above the waves. This one-way connection ensures the vessel remains a silent ghost, waiting for a signal that everyone hopes will never come. But while the SSBNs wait, 4 of their sister ships have been modified for a much more active tactical role. While the majority of the Ohio class remains dedicated to nuclear deterrence, of 4 specific hulls, the Ohio, Michigan, Florida, and Georgia, underwent a radical transformation. Following the START II treaty, the Navy converted these ballistic missile ships into SSGNs, or guided missile submarines. Instead of 20 nuclear missiles, these ships now carry up to 154 Tomahawk cruise missiles. Each of the massive missile tubes was modified with a multiple all-up-round canister, MAC, allowing a single tube to hold 7 Tomahawks. This gives one submarine the strike capacity of an entire surface destroyer squadron. Beyond the missile payload, the conversion turned these submarines into elite, clandestine motherships. 2 of the 24 original tubes were converted into lockout chambers for Navy SEALs. These chambers allow divers to exit the submarine while it remains submerged, often deploying from dry deck shelters, DDS, mounted on the submarine's exterior. These shelters can house sealed delivery vehicles, SDVs, miniature submarines that transport special operators even closer to a hostile coastline. These blue and gold crews transformed a nuclear deterrent into a tactical strike platform. But can a Cold War hull survive modern shallow water detection? In the congested waters of the 21st century, the massive size of the Ohio class becomes a liability. While it dominates the deep ocean, the next evolution of the American submarine fleet must address a new technological reality, a move away from mechanical gears and toward a silent, all-electric future. The U.S. Navy is currently transitioning from the Ohio class to the Columbia class at a $132 billion program that represents the most significant leap in submarine quieting since the Cold War. While the Ohio class relies on mechanical reduction gears to translate high-speed turbine energy into propeller rotation, the Columbia class utilizes an integrated power system, IPS, with an all-electric drive. In this configuration, the nuclear reactor powers turbo generators that produce electricity, which is then sent to a permanent magnet motor to drive the shaft. By removing the massive mechanical gears, engineers have eliminated the primary source of tonal noise that enemy sonar traditionally tracks. The Columbia class also introduces a life-of-the-ship nuclear reactor core. Unlike the Ohio class, which required a mid-life refueling overhaul that took the ship out of service for over 2 years, the Columbia's reactor will operate for its entire 42-year lifespan without ever needing to be opened. This engineering breakthrough allows the Navy to maintain the same level of global deterrence with only 12 Columbia-class submarines compared to the 14 ships required in the Ohio fleet. To further enhance stealth, the new class features an X-shaped stern for superior maneuverability in shallow water and a pump jet propulsor that significantly reduces acoustic cavitation. Every component of the Columbia class, from the 560-foot hull to the 16 missile tubes, is designed with a focus on modular construction and digital maintenance. The transition to electric drive not only makes the ship quieter, but also provides a massive surplus of onboard power. This energy will support advanced sonar arrays and future defensive technologies that require instantaneous high-voltage electricity. The U.S. Navy is spending $132 billion on 12 new ships, but will the move to all-electric drive finally make the submarine truly undetectable? The Columbia class ensures that the silent vigil continues, pushing the limits of physics to remain the most survivable weapon system on Earth. As the first hulls of this new class enter the water, the ocean remains the ultimate high-tech battlefield, where the winner is the one who is never heard. The true engineering triumph of the ballistic missile submarine is the acoustic advantage. By mastering the physics of sound suppression, using rubber-isolated rafts, anechoic coatings, and now all-electric propulsion, engineers have created an 18,000-ton machine that is literally quieter than the movement of the ocean itself. This breakthrough transformed the submarine from a simple weapon into a strategic ghost. It is the only platform in the world capable of holding an entire continent at bay while remaining completely invisible, ensuring that the balance of global power rests on a foundation of a silent, underwater stability. The evolution from the Ohio to the Columbia class marks a shift from mechanical power to digital dominance. These vessels are the most complex machines ever built, requiring the perfect synchronization of nuclear physics, structural engineering, and acoustic science. As long as these silent sentinels remain hidden in the deep, they fulfill their primary mission, ensuring that the most powerful weapons in human history are never used. Machines like this continue to redefine the balance of power in modern defense strategy. The story doesn't end here. Tell us in the comments, which military machine should we explore next? Fighter jets, submarines, aircraft carriers, or secret military bases? And don't forget to tell us which country you're watching from.